Okay, so with neutralization reactions, let's start like just kind of generically. So in general, a neutralization reaction, for this class at least, is always going to involve an Arrhenius acid. So Arrhenius acid, and then a Arrhenius base, which means we're very specifically going to have that OH in it because Arrhenius bases directly contribute to that. So I'm going to put just a plus because it's going to be some type usually of metal or a polyatomic ion with a positive charge in front of it, because we're just talking generically right now. So we have our Arrhenius acid, our Arrhenius base, and then we're going to make from that water and a salt. And a salt, remember, is just a word in chemistry for an ionic compound. So this is created, this is a double displacement when the hydrogen here joins with the hydroxide over here, when the H plus from the acid reacts with the hydroxide from the base. This is a really, really favored reaction, as we've kind of seen and talked about, the hydronium reacting with the hydroxide to make water. So that's where the water comes from, is from the hydrogen, whatever the acidic hydrogen is from the acid, and the hydroxide from the base. Now, if there's more than one hydrogen here, if it's a polyprotic acid, so if it's an acid that can give off more than one hydrogen, I would recommend don't worry about that. You know it's going to make water. One hydrogen is going to react with one hydroxide to make water. We might make more than one water molecule, so we might end up with some coefficients here, question mark. But don't try to bring that over. And I see that a lot, where if this has a 2, then suddenly we get weird hydronium type things here. Hydronium is not remotely neutral. In fact, hydronium is considered a very strong acid. So neutral is water, so a neutralization reaction is going to make water. So that's the first kind of step is, okay, we know we're going to make water, and we know we're going to make a salt. The big thing is, what is the salt going to be? What is it going to be, and how do we write its formula correctly? So the salt is always going to be composed of the cation, the positive one from the base. So this is our cation, and by convention, especially with inorganic compounds, we write the cation first. So I'm going to bring that cation over, just whatever its symbol is. I'm going to bring it over here. So this is going to be the cation from the base. And then I'm going to grab the anion, the negative one from the acid. And that might be something like, it might be a single element like fluorine, or it might be a polyatomic ion that we know is negative. But the anion from the base, the negative one from the base, so in this case I had drawn it as A, so A, the anion, sorry, from the acid, the anion from the acid is going to be the anion of our salt. And so I would say just take them over and put them together. But then remember, back in, I think it was Unit 2, when we learned about salts, one of the things we learned is that they always join in a ratio that overall is neutral. So we have to figure out what's the correct formula of this salt. So after we've just brought them over, then we have to go like, okay, but is that the correct formula? Do not just carry over subscripts unless it's a polyatomic ion. So if this is like PO4, yeah, definitely bring over the 4. But if it has a 2 around it, we shouldn't assume this one is going to have that. We just want to bring over the polyatomic ion and then ask ourselves. So then we're going to go like, okay, but is it neutral? How do we write the correct formula to make it neutral? So neutral formula, because that's just how you write the formula of salt. So this, what is the correct formula? And then, and only after we have done that, do we go back and balance and consider, oh, but we have a polyprotic acid, so we need to make more than one water. And this formula over here, we have 2 sodiums, but we don't over here, something like that. So let's put this into practice. Let's like look at a neutralization reaction. So let's look at sodium hydroxide might react with Oh, let me see. What one do we want to use? Let's do a polyprotic one. So we have to kind of consider that. We'll do sulfuric acid, H2SO4. Okay, so taking a look then, you'll notice that I listed my base first. There's no rule or convention that the acid has to be listed first. So you have to, okay. But I can tell it's a base because it's a metal hydroxide. And we know that those are our strong bases. So we have an Arrhenius base, an Arrhenius acid. And so I'm going to immediately jump into that first mode of going, I know I make water from this. Now there's 2 hydrogens here, but I'm not going to worry about that until later. I know I make water. And that water is being created from hydroxide ions reacting with hydrogen ions that are being donated. Now I want to go, but what's my salt? So my salt is going to be made of the cation of my base. So find your base. And these are always, for this class, these are always going to be Arrhenius bases. So it's the one with the OH, right? Okay, so the cation is sodium. So I'm just going to put sodium over here, Na. And then the anion for my acid. And if you kind of think about things you've accounted for, you can kind of do that and go like, okay, these are my things that are left. Now, a thing to remember is this whole thing is a polyatomic ion. So I need to bring over the whole thing. So SO4. So I've created at least a kind of like base, a foundation for what my salt is. My salt looks like sodium sulfate. But is that the formula of sodium sulfate? If this were a different question that just said, what's the formula for sodium sulfate? Is that what I would write? Well, not if I wanted to get the answer correct. So now we need to, let's do this work somewhere kind of else. Now we need to do the work of determining what the correct formula for sodium sulfate would be. So sodium is sodium ions have always a very standard charge of +1. We know that from the number of valence electrons they have. We know that from where it sits on the periodic table, which is related to how many valence electrons it has. And sulfate is a polyatomic ion that really just through the sheer force of memorization, we know is a -2 charge. So I can see this is not balanced. The -2 is not canceled out by a single sodium. I need a second sodium because now together that can cancel that out. So the correct formula for my salt needs to have that little 2 there so that I am going with a neutral formula. That's the correct formula for sodium sulfate. Now that I've done that, I want to go back and balance my chemical equations. You can see how neutralization reactions really build on a lot of different concepts from a lot of different units. We're really synthesizing things together, which makes me love them as an instructor because I'm like, wow, this is a great opportunity to pull from unit 1 and unit 2 and unit 3 and unit 4. We got all those things going on. So in terms of balancing, I like to start with my my salt just because that's often the place that the balancing can get. I just find it a little bit easier. I'm going to change colors here. So I see that I have 2 sodiums, but I only have 1 sodium ion accounted for on my reactant side. So I'm going to put a 2 in front of there. And this is actually going to be helpful because that 2 multiplies the oxygen and it multiplies the hydrogen too. And I kind of needed that for the fact that I have this 2 over here. So if we want to like paying attention to hydrogens and oxygens, over on my reactant side, I now have 1, 2 hydrogens, 3, 4. So I have 4 hydrogens over here because I have 2 in my polyprotic acid, and I have created 2 in the balancing of this portion because that 2 multiplies the hydrogen. And in my oxygens, now I actually have more than 2 oxygens, but I've already taken account, this oxygen over here isn't a part of the neutralization. It's a part of the salt. So I'm not going to pay attention to it. So when I say I have 2 oxygens, I'm really referring to the oxygens that are going to make the water. So looking then over here at my product side, I have a really nice way to fix that because right now I have 2 hydrogens. And again, I'm not paying attention to anything over here. I'm only focusing on the creation of water. And I have 1 oxygen. This is nice because look at how you can tell. Oh, if I put a 2 in front of that, I change this to 4 and I change this to 2 and it is now balanced. So in a neutralization reaction, the important thing to remember is you're going to make water and salt. So I would say, make sure you put water. Then after that, figure out what your salt is going to be. Your salt is always going to be composed of a cation and an anion because that's what salts are, right? So find the cation and anion that aren't involved in the making of water. And that is going to be the cation, the positively charged one of your base, and the negatively charged one of your acid, whatever that may be. That might be, if you're working with, what's the word I'm looking for? Hydrofluoric acid, that would be a fluoride ion. If you're working with phosphoric acid, that would be the phosphate polyatomic ion. So, and then the anion, the negatively charged one, it can't be hydroxide, right? Even though we know hydroxide is a negatively charged particle, it can't be hydroxide because hydroxide went to make the water. So it has to be the anion of our acid. So we're always going to be joining the cation of our base with the anion of our acid. But then we do need to make sure we write that formula correctly. That, you know, each salt has its own formula. So a salt we have on the reactant side, we can't turn around and assume the same ratio on the product side. We have to do that mental work of going, how many of each do we need to make neutral? And then after we've done that, we can go back and balance. One thing I've noticed over the years, and I'm not sure the pattern holds true 100% of the time, so be careful. But if I'm having trouble balancing, I've noticed that a lot of times for these, I have a polyprotic acid. So if I have more than one hydrogen that can get donated, such as in sulfuric acid, or phosphoric acid can actually donate 3, which is kind of cool. A lot of times that subscript will end up being my coefficient here in front of my water. So if you're having trouble balancing, you might want to try that out. Now that didn't account for this one. I still needed another coefficient to make it balanced, but it can help you a little bit with your waters, making sure that you're creating the proper number of water molecules. So each mole of sulfuric acid in this case will generate 2 moles of water. So hope that makes sense. Keep the questions coming.